For more than 100 years, Schneider Electric has been an industry pioneer of market-leading solutions. As the engineering landscape rapidly changes, no one feels the impacts of the mounting challenges like consulting engineers. We understand these challenges. We face and solve them with you every day. Projects are becoming more complex, faster moving, and the connected world demands immediate answers while margins grow tighter. As an expert in your own right, we're set on making sure that you're equally matched in the manufacturing company you turn to, which is why we're launching Proficient for Consulting Engineers, a suite of services and tools that gives you unparalleled control from design to implementation, solidifying a real connection between highly qualified professionals. Proficient is built on a foundation of E2E, or expert to expert. Through innovative technology, responsiveness, and industry-leading BIM advancements, Proficient is tailored for you. All backed by market-proven Square D and Schneider Electric products with matchless service and support, we're delivering expertise that enables you to excel. You spoke, we listened. Proficient for Consulting Engineers. Expert to expert.
Welcome, everyone, to the Proficient for Consulting Engineers and our Expert to Expert webinar series. Today's webcast is sponsored by Schneider Electric and its various brands, including Square D. I'm Wendell Leisinger, Segment Manager for the Consulting Engineers, your moderator today. Today's topic is Power Harmonics. But before we get started, I'd like to share with you a little bit of things that are going on with our Consulting Engineer portal. You will be able to receive continuing education credit via the portal, which is our Consulting Engineer portal that you need to log in and register for. It also gives you direct access to numerous tools like Layout Fast, our BIM models, design applications, and more importantly, even product specifications. Also, we'd like to keep you up to date in products and solutions and give you a needed edge in your designs. Please log into the Consulting Engineer portal. A little bit about today's webinar and the dashboard that you have in front of you. On the bottom, there are several icons. The first icon, there's a yellow box that controls your slides. That's the one that is turned on your slides. As a matter of fact, in the top right corner of your slides, you can click that and enlarge the slides for viewing pleasure. The green resource folder is where you'll be able to download this presentation, as well as a link to our Proficient for Consulting Engineer website. And you can create also the PDH certificate off of our portal. If there's any questions or concerns, please refer to this green resource folder for a hot link that would get back to us about the certificate that you're downloading. You can ask questions on that Q&A red button anywhere during the presentation. I will be reviewing these as a moderator and teeing them up for our presenter. Depending on where the presenter is, these questions may be held for a little while, but in any event, we'll get to your questions. And if we don't get to all of your questions through this webinar, we will answer them offline later. And also, this webinar is recorded for your viewing pleasure afterwards. There's a survey button that we would really appreciate your feedback about this webinar and its use and value to you, such that we can enhance our expert to expert webinar series as we continue going forward. Also, we have social media links for Facebook and LinkedIn. And please remember again to give us your feedback by answering the survey that can be done anytime during this presentation. And also, we will keep the webinar open for 5 minutes afterwards so that you can complete your survey. Before we get started, we'd like to know a little bit about you. Here's a polling question that, if you would please, what is your knowledge level regarding power harmonics? Are you an expert or are you a novice? give us a little bit of background that'll help us through our presentation. Let's take a look. So we see that many are familiar. There's a few novices and a few experts. Great. Let me talk to you a little bit about the outcomes or learning objectives for this particular webinar. First, we'll give you some basic understanding of electrical terms and definitions. We'll also dive into IEEE 519, not only why it's required, but updates. Then we'll be talking about harmonic solutions versus power factor correction solutions. And also, you'll be able to identify harmonic application. With that, I have another polling question. Of these four, electrical terms, IEEE, harmonic solutions, harmonic applications, which ones are of greatest interest to you today? I see many of you have answered. Great. Harmonic solutions and power factor correction. I personally had thought that maybe the team on this webinar would be very, very interested in that. Great feedback. With that, I have one last question. This polling question is about the market that you're working in. In other words, your designs are for food and beverage, healthcare, data centers. Give us your world, or let us know a little bit about your world so that we can tailor any of the presentation or questions to your particular marketplace. Let's take a look. Healthcare and office buildings, great. There's a few others, but we'll be able to now we understand, we'll be able to tailor this presentation to you. With that, I'd like to introduce Brian Tofton. Brian is our Power Harmonics Solutions expert. He resides in Southern California. His contact information, including his LinkedIn information, is on this slide. Brian will now take us through the Power Harmonics webinar. All yours, Brian, and welcome.
So thank you, Wendell and his team, for everything going into today, and thank you for everyone out there for your time and joining the webinar. With that, we'll go ahead and jump right into our first topic, which is electrical terms and definitions, which will give us a foundation for our power harmonics discussion today. Then we'll cover several power harmonic terms from the categories of types, power types of reactive power, and how it defines harmonics that may be applicable in your systems today. So some of the first three basic terms that I'd like to cover are going to be the following terms, which are typically used when discussing AC power and harmonics. First one is real power, which is the power that does the work. It is required by all applications and is supplied by the power source. The second one, and one that we'll focus largely on today, is reactive power. It is the power that is sometimes required by applications. Example would be AC motors to permit real work to be done. Many times, as in AC motors, inductive reactive power is required to create the electrical field that permit the real work to be done. And then lastly, apparent power, which is the root mean square of the real power and reactive power. Moving next to further types of reactive power. First, we have phase shifted power, which can be leading, typically caused by capacitors, or lagging, caused by inductors. This always occurs at the fundamental frequency, typically 50 to 60 hertz, and is commonly defined as the displacement power factor, also known as DPF. And this is typically what the utility charges penalties for, again, depending on your local utility and your geographic location within the U.S. Second is harmonic power, which is caused by rectifiers, also known as converters, which is the change of power from AC to DC for use inside the product. It is typically defined as the distortion factor, DF, and generally harmonic discussions refer to percent THDI or percent THDV, which I'll get into a little more as we proceed in this discussion, to indicate both harmonic amplitudes, which is a total harmonic distortion current as a percent, as well as the total harmonic distortion voltage as a percent. The next two, which I don't want to spend too much time on, I really want to focus on both phase shifted power as well as harmonic power, but for all intents and purposes, I'd like to quickly review the definitions of both negative sequence power, which is caused by single loads connected to neutral or phase-to-phase on a three-phase source. The result is unbalanced power flow per phase. As far as AC motors are concerned, negative sequence power causes reverse torque, and much damage could be associated with that. And it also manifests itself as unbalanced current on a three-phase supply. And then lastly is zero sequence power, is a result of single-phase loads attached to neutrals. It typically refers to harmonics on the neutral conductor. They're also called triplet harmonics. And again, we'll get a little bit more into that later with some applications because of the harmonics are multiples of 3 added directly on the neutral to massively amplify the harmonic currents on the neutral conductors. So further breaking down some of the phase-shifted power, I want to start with two different types. The first is going to be lagging power factor, which is the measure of current phase shifted, typically caused by inductors, where the current lags behind the voltage and is shown as a positive number between 0 and 1. And the second is leading power factor, the measure of current phase shift, typically caused by capacitors, where the current leads in front of the voltage and is shown as a negative number between 0 and -1. Okay, next we'll get into, again, these are fairly basic definitions, but we'll cover them for purpose of discussion. Resistance, which is a measure opposite of the current flow, which is typically a resistor, and there's no phase shift induced. Next is inductance, which is measured as L, and this is the measurement of resistance to current flow through a coil inductor, typically causing a lagging power factor. Third is capacitance, which is a measure of the ability to store voltage, typically in a capacitor, causing a leading power factor. Next is reactance, which is the measure of combined effects of resistance and inductance. And then lastly is impedance, which is very prevalent for our discussion today, and it is the measure of combined effects of capacitance and inductance, and then the percent impedance. And the formula equation is shown accordingly for everybody who's interested. Okay, so moving on to our next section, we'll discuss IEEE 519, the standard which originated back in 1992, and some of the revisions just made last year, moving to IEEE 519 2014, as well as several key terms such as PCC, PDD, and THDV. And as stated by IEEE, the IEEE 519 standard is the recommended practice and requirements for harmonic control in electrical power systems, which, again, by their definition, it sets parameters for the design of electrical systems that include both linear and nonlinear loads are established in this recommended practice. So IEEE 519 standard. So first question is why is it required? The method for handling harmonic specifications to date has really been somewhat subjective. And per IEEE, their definition is it sets parameters for the design of electrical systems that include both linear and nonlinear loads are established in this recommended practice. The voltage and current waveforms that may exist throughout the system are described and the waveform distortion goals for the system designers are established. The interface between sources and loads is described as the point of common coupling, also known as PCC. And observance of the design goals will reduce interference between the electrical equipment. The typical error lies in specifying the PCC and objective levels of THDV or TDD. The specific methods of calculation typically widely varies, part of the reason why the standard was originally set up in 1992. And it is required to verify that compliance has been designed into the equipment, provided harmonic analysis is the only method that can verify the true compliance. However, each vendor will typically be held responsible for their respective equipment, where the compliance lies at the system level for IEEE 519. So going back to some of the original goals for IEEE 519 1992 has been the harmonic standard used typically in North America since the latest revision in 2014. And their primary issues it addressed was the voltage distortion delivered by utilities to users, which is shown in the standard in Chapter 11. It requires the 5%, under 5%, and then for a under 69 kV system. The second major issue is TDD, which is also known as total demand distortion, which is the harmonic current distortion at full load, also known as THDI, that users may cause on the utility, again found in Chapter 10 of the standard, which is the size of the user in relation to the power source. Third, it defines the limits of voltage notches across the SCR rectifiers, which is shown in the standard on Table 10.2, which we'll discuss in the upcoming slides. And then lastly, the PCC, also known as the point of common coupling in 1992. And at that point, their definition of PCC was the recommendation described in the system document attempts to reduce the harmonic effects at any point in the entire system by establishing limits on the certain harmonic indices, currents and voltages at the point of common coupling, a point of metering or any point long as both the utility and the consumer can either access the point for direct measurement of harmonic indices meaningful to both, or can estimate the harmonic indices at a point of inference, POI, through mutually agreeable methods. With an industrial plant, the PCC is the point between the nonlinear load and other loads. So moving on to some of the recent standards to IEEE 519, as recent as just last year, 2014, the standard dating back roughly 20 plus years or so was used. And what this really addressed was distortion levels below 1 kV. The THDV must be less than 8% on a less than or equal to 1 kV system. For medium voltage and high voltage services, the limits are the same as the 1992 standard. Low voltage service voltage distortion limits were 5%, and those are now raised at 8%. And the current distortion remains the same as in IEEE 519 1992. Okay, so next we'll get into the point of common coupling with the and some of the definitions there. With the consumer and the utility interfaces is basically the closest point on the utility side of the customer service, where another utility customer is or could be supplied. The ownership of any apparatus such as a transformer that the utility might provide in the customer system is immaterial to the definition of PCC. So for the 2014 standard, IEEE defines it as the limits in this recommended practice are intended for applications at the point of common coupling between the system owner or operator and a user. The PCC is usually taken at the point in the power system closest to the user where the system owner or operator could offer service to another user. Frequently, the service to industrial users, i.e. manufacturing plants, through a dedicated service transformer. The PCC is at the high voltage side of the transformer. For commercial users, office parks, shopping malls, etc., supplied through a common service transformer. The PCC is commonly at the low voltage side of the service transformer. So moving on and defining the TDD, again also known as total demand distortion, which is the harmonic current distortion level at maximum or demand load for the facility. The THD, the total harmonic distortion, is a term used for voltage distortion measurements. And by definition of IEEE 519, 2014, they state the ratio of the root mean square of the harmonic content considering harmonic components up to the 50th harmonic order, and specifically including interharmonics expressed as a percent of maximum demand current. Harmonic components of order greater than 50 may be included when necessary. And this is certainly an improvement from the standard dating back to 1992, where they defined it as total demand distortion, harmonic current distortion in percent of maximum demand load current. So taking a further detailed look into this and more of a field application approach, the chart that we provided below shows basically the difference between THDI and TDD. The blue highlighted area is what the harmonic analyzer measures, and which we actually reported on a DC load at our plant in Salem, Oregon, as it is a production facility where we manufacture our active harmonic filters. And please note that the amplitude of the harmonic current decreases as the load decreases. So however, for THDI, which is the harmonic current divided by the fundamental current at the time of the measurement increases, the harmonic current decreases. So in conclusion, what we see is that if your electrical system can handle the harmonic current at FLA, then it can handle the harmonic current at any other load point because it is less than full load.
So Brian, there was a question about THDI. If you could just repeat what the definition of THDI is.
THDI is the total harmonic distortion measuring current, and it is equal to the TDD at full load. However, this changes once the FLA is backed off.
So we have another question, more acronyms, but are there any standards for gensets at the PCC? Generator is owned by others and supplying power to the customer.
That's a very good question. One that I can certainly follow up on a little later, because I think that's a pretty detailed discussion, and I'd be very interested in having. But I'd like to pull the conversation back to more of the Harmonic Solutions approach.
Okay, thank you. And one last question, maybe you're going to get to this. Are 18-pulse drives a common harmonic control solution versus line filters, drive line filters?
Another great question, and I will spend the next 25 minutes discussing that.
Thank you.
Okay, so moving to our next section, we'll discuss some harmonic solutions. And we'll cover some various harmonic solutions, including both passive and active filters, and the pros and cons of using each device. And really, where the complexities are added from a total system standpoint. And we will use a standard 6-pulse VFD for the purposes of the discussion. Okay, so starting off here with Harmonic Solutions. Solutions are selected based on several factors, which are short circuit current capacity, rectifier devices employed, converter design, i.e. 12-pulse and 18-pulse drives, built-in inductance, capacitance, internal and external filters, and added inductance at rectifier. And one thing I want to note here is that every solution really has its place per application. And every solution typically has its complexities, whether it be added equipment costs, which equals added costs, added heat losses, additional cooling requirements, larger footprint, which would be needs for more space, added installation complexity costs, or additional power cabling with the current transformers, and application performance may be applicable, as well as too much impedance loads performance. So generator interaction difficulties, speed of change of current over time. And we'll get into kind of a breakdown of what the current solutions out in the marketplace and how they affect each of the following categories discussed. So, per the question a few minutes ago, there are 3 types of phase rectifiers, converters, commonly used today. Each type has different levels of harmonic and DPF on electrical system. We'll discuss each in the following slides in great detail, but in short, the thyristor, the SCR, controlled rectifier, highlighted in green. The second is a diode, which is the uncontrolled rectifier, and the third is the Igbt, bidirectional controlled rectifier, which we'll spend a good portion of our time discussing, and this is commonly called a active front end. Okay, so jumping right into it, the first solid-state rectifier device deployed, which is still in use today, are thyristors, also known as SCRs. This device is used to provide a precisely controlled power flow into DC bus from the product. The 3-phase thyristor typically uses a lagging power factor when not operating at full load amperage. The DPF tends to get worse as the load increases. Also, harmonics are caused in the rectifying process. Harmonic current amplitudes are typically worse at full loads. And the third effect is that the process of turning of a conducting device, a short circuit momentary occurs on the AC lines. This causes voltage notch, as seen above. And this is a direct THDV problem, which reduces inductance on the AC lines side of the thyristor to reduce the notch depth. One type of equipment employed in thyristor rectifiers is your pretty common DC drive. Okay, so next we'll move on to a 3-phase series controller. This is basically, the 3-phase controller controls the amount of current let through the load side of the device. The result of the DPF at expected at full load levels in the harmonics that get worse as the load is reduced. One very common use for a 3-phase controller is actually a solid state starter, commonly known as a soft starter. For AC motors, and this typically helps reduce peak current draws from an AC motor for difficult to start loads. And based on the limited use of the soft starters, only operate for seconds, they typically are not considered a harmonic or a DPF problem. But when the AC motor is the predominant load on the AC supply, both harmonics and DPF may be required for reducing. So another type of three-phase controllers are the inductive and resistive heaters. The intention of the heaters is to manage the load flow to maintain heating levels in the loads. These may operate at reduced load flows for long periods of time. Thus, the DPF and harmonics must be addressed. Same thyristor configuration as the SSS or the soft starter. Different when used as compared with the soft starter, as it's designed to control current through resistor banks and inductive coils to control heating. And typically what you see is high harmonics, except at full load, and very poor power factor, again, except at full load. Okay, next we'll get into a three-phase rectifier, which is a diode rectifier, which always conducts when an AC voltage is higher than the DC voltage. There are no DPF issues. It typically operates around a PF of 0.98 to 0.95, and the harmonic amplitudes are highest at full load. Percent THDI is lowest at full load. Harmonics are concentrated in the 5th and 7th harmonic order. Higher orders of harmonic occurs when there is no or very low inductance at the rectifier, either AC or DC side. As shown above, lack of inductive impedance causes very large amplitudes at higher harmonic orders. Typically, you see this in devices like a UPS or a VFD. And as you can see in the chart, there's substantial drops within the graph below. So next, we'll move on to a three-phase Igbt rectifier, also known as an active front-end converter. And this is typically the newest design of a rectifier that uses Igbt devices, which are devices that permit current control in both directions, AC to DC and DC to AC. Different control logic can be used to create different levels of current control between the load and AC lines. Two methods primarily in the low harmonic mode of control that are used for pump and fan applications, and the active front end does the following. It maintains the current on the AC lines to look like the above current. The voltage is forced into a square waveform, and the percent THDI is low, but the percent THDV is very high. And in the fourth quadrant mode, the logic controls the current flow to maintain the DC bus voltage within the design levels to optimize the load control. This means the current can look like a diode rectifier at times and similar to what's shown at other times. The result is that the percent THDI varies between high THDI and low THDV. The typical application for a VSD is a downhill conveyor or large machinery production tools. And voltage distortion can be fixed by the active front-end designer. In the coming slides, we'll discuss the measures required to the limit percent and THDV for the active front-end VFD. Okay, so next we'll move into a single-phase rectifiers. It can be used phase to neutral or phase to phase. Both are identified as switch mode power supplies, also known as SMPS. The diode rectifier typically exhibits high levels of harmonic currents causing high percent THDI, where DPF is fixed at new unity. The switch mode power supplies connected phase to neutral cause very large levels of tripling harmonics on the tripling. And again, for purposes of definition, tripling is basically the odd multiples of the third harmonics. So for example, the 3rd, 9th, 15th, and 21st, which can lead to very high current circulating on the neutral. and unless the neutral is sufficiently oversized, this could present a pretty significant fire hazard, or just in general, oversizing your equipment. So next, the newest type of switch mode power supply is a buck boost converter. The converters are intended for reduced percent THDI levels to very low amplitudes of less than 5% THDI, eliminating neutral harmonic issues, and standard size neutral cables can be used again. At FLA, they produce a DPF of a leading 0.98, normally written as negative 0.98 as it's a leading power factor, with a harmonic current level of about above 5% THDI. However, one concern with this is that the load is reduced from FLA. The capacitor continues to inject the same leading current since it cannot flow into the switch mode power supply. It actually flows to the AC lines, thus resulting in even more leading power factor as the load drops. Then the leading DPF is treated as the same lagging DPF by utilities and still penalized, again, based on the standards set forth by your local utility. So, in short, as we continue our discussion, the next couple solutions I'll really focus based on a 6-pulse VFD drive, and then I will do several comparisons to both passive and active filter solutions, and basically the current designs out in the marketplace and how they compare based off your applicable system. So first, we'll discuss the reduced harmonic designs, which is CLIS. Then we'll get into the passive filters, so added inductive impedance, fifth harmonic filters, broadband filters, multi-pulse transformers and inverters, and then we'll discuss quite intensively the active front-end converters, and then we'll get into some active harmonic filters. They can be applied to both single, nonlinear, and multiple nonlinear loads.
Brian, before you start, do you have a little bit of time for questions?
I do, yes.
What is DPF?
DPF is displacement power factor.
Okay. One comment came in, maybe I missed it somewhere, but if the IEEE 519 point of coupling is on the high voltage side of the transformer, why are we required to find solutions for harmonics at a motor 4 levels downstream? If there are no real issues.
Very good question. And IEEE 519 is both applicable to the utility as well as the facility or end user. And I can certainly have a more detailed discussion on that, but both stakeholders are the utilities as well as the local facility and end user, and so they are both affected.
Excellent. Here's a question. What about products that suppress harmonics instead of filtering? They, Harmonic Limited, claim that they prevent the third harmonic currents at the source.
Okay. Very good lead-in question for my next couple slides, and we'll get into a pretty detailed discussion on a couple products that we have for both suppression and what some of those technologies do, not only within the 5th and 7th harmonic, but what are the effects of suppressing the 5th and 7th harmonic and increasing, whether it be the 37th or 41st, and really how that looks like as a total picture as opposed to just looking at a couple harmonic orders. So in short, we will discuss that in some detail in the next few slides.
Excellent. Thank you, Brian.
So as mentioned, great lead into our next topic, which is reduced harmonic technology. which uses less capacitance in the DC bus to reduce the overall percent THDI. The total harmonic distortion levels are in the range of 35 to 45% THDI, similar to adding inductors to a pulse VFD. The DC capacitors are replaced with the new DC caps to handle majority of the voltage cycling for extended product life cycle, which adds no heat losses to the VFD. So if we take a detailed look into the graph shown below, what we see on the standard pulse drive is very high 5th and 7th harmonic currents, while the reduced harmonic technology, as denoted in RHT VFD in purple in the graph, has a very flat harmonic current amplitudes and very high, relatively speaking, to the standard pulse drive at the 41st and the 43rd harmonic orders, i.e. not meeting IEEE 519 compliancy. So in essence, what IEEE 519 does is not only look at the 5th and 7th harmonic order, they look at the harmonic order through the entire use of the product. So you truly need to look at the system level and really monitor the device, not only at initial startup, but really look at it amongst the later harmonic orders and to really see how your system is interacting at that point as well. Okay, so moving on to the next section is going to be inductors, which we'll discuss and how that interacts in the system. And again, for purposes of discussion, we're going to compare most of these solutions to a standard 6-pulse VFD drive. So adding input impedance or a DC choke to a standard VFD will still be similar total harmonic distortion current as reduced harmonic technology, as shown in the previous slide, with a 3 to 5% impedance, and the input and DC bus inductors may be used on the same device. So basically, we're adding inductors, heat losses, and the cost, in all cases, usually small amounts. However, the results for reducing the THDI are about 100% to 35% with a 3% line reactor. And this technology really has no application limitations, and the additional benefit here would be a input line reactor suppression of the AC line voltage transient. So another commonly used harmonic solution would be a dedicated 5th harmonic tuned filter, which greatly would reduce the percent THDI to about 20% with a fairly moderate heat losses to 2 to 3%. And this filter can approach or exceed the size of the VFD which they're applied to. So if footprint is of an issue, typically this would not be your best solution. And some of the application limits we see are the possible generator issues due to high capacitance in the filter, whereas they need to add more filters for each harmonic order. So essentially adding capacitance. And if you look at IEEE 519 as strictly followed, you'll see some of the harmonic orders past the 5th and 7th will not comply per the standard. So moving on to broadband filters, which offers a percent THDI reduction and can obtain levels as low as 5 to 10% THDI. These filters tend to have a very large footprint and actually exceed the physical size of the VFD on which they're applied to. And their heat losses are slightly higher than the 5th harmonic tuned filter. Due to the large series impedance, these filters tend to be limited to use in pump and fan applications and to a standard pulse VSD. Some of the application limits may have negative may be negative on backup generators, as they can cause excessive capacitance and produce a leading power factor, as well as voltage impedance. So performance levels are only for unbalanced to 2%. Very low typically, and the AC systems can certainly have a much higher impedance. Okay, so moving on to both multi-pulse drives. Primarily, we're going to talk about 12 and 18 pulse rectifiers. Multi-pulse drive is really been around for a very long time, from the 50s. At that time, they were typically used to increase the size loads for the diverse rectifiers that could handle. Then in the 1990s, the multi-pulse reemerged as harmonic reduction applications. So if we take a look into a 12-pulse configuration, employ 2 rectifiers of any design in a transformer, auto or isolation, which has 2 secondary windings that have a 30-degree phase shift when applied to a single load, every other odd pair of harmonic orders is greatly reduced. This begins with the 5th and 7th harmonic order. A 12-pulse system can attain 12% THDI, typically per load. Now, moving down to a 18-pulse configuration, they typically employ 3 rectifiers, a transformer with a 3-phase shifted second windings at the 20% phase shift. This results in canceling 2 pairs of odd harmonic orders and leaving the 3rd unchanged. This greatly reduces the 5th and 7th harmonic order pair, as well as the 11th and 13th pair, and leaving the 17th and 19th pair. When applied on a single load, about 5 to 75% THDI can be attained. Both solutions are fairly physical large with the auto transformers. It essentially doubles the size, again, as we're using the benchmark as a standard 6-pulse VFD. Due to rising cost factors, as the size of the VFD is reduced, they are not typically applied below 75 kW or 100 horsepower. However, when the load is reduced, the input current typically goes unbalanced on the secondary windings, reducing the percent THDI benefit. So when the AC goes unbalanced, the percent THDI reductions are minimized, thus having a fairly poor percent THDI results. And as far as application limits with the multi-pulse drives, there's really no limits. As far as voltage impedance, added losses of 2 and 3% are typical within auto transformers. So if we take a step back and take a look at both the waveforms of a standard 6-pulse converter, 12-pulse converter, and an 18-pulse, what we show is the waveforms. And so focusing our attention to the 6-pulse, you see the current waveform distorted at TDD 30% to 40% with the 3% line reactor. And again, all of them depend on network impedance. But as you can see, that's a very choppy waveform, and you're getting quite a few harmonics on the line there. So if you move our discussion to the 12-pulse converter, current slightly is distorted TDD at 8 to 15%, again depending on network impedance. But you can see the waveform is improving. However, it is still fairly choppy, as shown in the graph there. And if we move to the far right, we can get a comparison against an 18-pulse converter, which shows a current waveform good to TDD 5% to 7%, again depending on network impedance. But the waveform does get much better. However, there's still some slight spikes in that form. And your TDD is, again, still at 5 to 7%. Okay, so moving on to some of the details of the active front-end rectifier, which are typically used in VFD and UPS applications. These could add a substantial footprint to your equipment as well as substantial cost to your overall system. And they essentially double the size of your current 6-pulse due to the incoming passive filters required to suppress the percent THDV and the high frequency switching noise caused by the Igbt. However, when used on a VFD for a pump and fan application or any variable torque loads, the logic is designed to maintain the Igbt switching to optimize the current draw as close to the sine wave as possible, achieving less than 5% DHDI. This also maintains near unity at DPF. The next slide we'll also discuss will basically get into what is needed for the active front-end rectifier to minimize percent THDV. And then, so kind of moving down to the far right of the slide, if the load is the constant torque application has 100% torque required from 0 to 1% speed, or a regenerative load, again, i.e. a downhill conveyor or a production machine or equipment, the logic no longer manages the active front end to attain clean power. The logic is designed to maintain the DC bus capacitor voltage to optimal torque control of the load. Sometimes the input current can also look as a diode rectifier, and a 5% THDI is not attained. There has also been installation of this type of active front-end VFD without the input filters, which we'll discuss in the next couple slides in some detail, which causes higher voltage distortion. Okay, so I don't want to spend too much time on this slide, but a few of the key takeaways of the active front-end converter, as I pointed out in some of the early discussions, is note the input filter is required to attain the THDV limits. It is a broadband filter, and heat losses are up to 3 to 4%, and the physical size is equal to the VFD size it's applied to. And the overall active front-end VFD efficiency typically drops to less than 95%, which is still strong, but you will potentially, depending on your utility, get charged for under 95%, whatever is stated in your local market, versus standard 6-pulse VFD with a line reactor, which is typically over 98%. And additionally, the capacitance always attached to the AC mains, even when the VFD is powered down. They'll have to be known to cause resonance on the utility substations. And in fact, in a couple cases, one I'll share with you guys in a few more minutes, is there's been a case where the LCL filter actually caught fire. And again, we'll discuss this a little more detail in a few minutes. But essentially, what I want to point out here at the bottom left is a capacitance connected to the mains at all times. So this can cause resonance on utility even when it is powered down. Okay, so real quick here, I want to point out this is typical wave harmonic orders for an active front-end inverter. And this is a study by the American Bureau of Shipping, also known as the ABS, requires examination to the 100th order when an active front-end is applied. So essentially, the higher frequencies yielding in higher heating of the current path and potential resonance due to caps, i.e. the 61st harmonic at 2.2%, and the heating as compared to the same level. So as you can see in the graph to the left, at the higher harmonic orders, you're actually getting a significant spike, almost double of what you would see at a 5th or 7th harmonic order. And again, this is per the American Bureau of Shipping, and typically how they do their compliance, which closely follows IEEE 519/2014.
Brian, our time is moving very quickly, so we have about another minute or two. Okay, very good. So I will move quickly through this next couple slides here, and just spend a real brief time covering the final application. So using more of a system approach, and again, some of the active harmonic filters typically can be used on one or multiple nonlinear loads, and reduced
The reduction here is a THDI to under 5% of the PF control to util is possible. This adds variable heat losses no more than 3%, as well as this does attain IEEE 519 2014 compliance even beyond the 7th harmonic order. So real quick, I just want to show you a sample that we've done, a test we run, and this can also be found under the resource tabs, which you'll be able to access following the presentation. And this is an example of a 600 horsepower VFD with the 3% line reactor tested without and with an active harmonic filter. And as you can see, the harmonic order jumps at the 5th, 7th, 11th, 13th, on down through the 41st and 43rd. And the total TDD is over 35% without the filter versus using the active harmonic filter, which you can achieve roughly 2.5% for using the active harmonic filter. Okay, I do have a case study that we basically have identified and worked through a couple different solutions, but for purposes of time, I'll quickly run through this, and Wendell, please let me know as...
We won't have time to do that. There is one question that maybe you can comment on, and that is, can you comment on the source voltage imbalance and its effect on mitigation of by 12 and 18 pulse drives? Source voltage imbalance and its effect on mitigation?
Yes, so really this depends on your application, and we are making some assumptions within this presentation. So, you know, to really identify a specific application, you know, I would certainly be willing to take a look at it. However, for purposes of discussion, we have made quite a few assumptions when comparing both the 6-pulse, 12-pulse, and the 18-pulse drives and their general waveform and the distortion levels.
Great, Brian. A great topic, and thank you very much for sharing your experience and insight with us. There are a number of great questions that we have not been able to answer, and there are some questions leading to potential webinars of the future. For example, we are planning on talking about harmonic mitigation transformers and other products in the marketplace. There are some other questions that we will connect with Brian and have him directly answer your questions. If there's any questions that you have or have not gotten a response to, please feel free to give me a call or contact me. I'm Wendell Leisinger, the moderator. And as I was suggesting, our next month's webinar will be on GIS, or gas insulated switchgear, and its importance into our market today. So stay tuned for the next webinar, gas insulated switchgear, in the middle of November. With that, I'd like to remind you that the continuing education credit and the certificate of attendance will be found on our portal, so please register on our portal. That portal gives you direct access to layout tools, models, and other design applications, and gives you an update. As a matter of fact, we thought we'd give you a short video at the end of this, in the next moment or two, that will highlight this valuable resource. With that, I'd like to say thank you, Brian, for updating us and sharing this information on Power Harmonics. And to the audience, thank you very much for attending. We look forward to seeing you at our next Proficient for Consulting Engineers Expert to Expert webinar series.
Today's busy consulting engineer needs more than just a helpful website. You need a trusted advisor and guide for insight and support. With our new Consulting Engineer web portal, Schneider Electric is just that, an expert source for product information, a seasoned second opinion, a layout specialist, a news and information resource, your own customized support system that makes you, your projects, and your business better. Product catalogs, technical support, codes and standards detail, specs, layout and coordination tools, expert insights, and industry updates are all as close as a simple click. Got a product question? access our enhanced digital version of the yellow binders you may have used in the past. Digest Plus gives you instant online access to Schneider Electric's entire product line, with technical, application, and layout information on our complete product catalog. Trying to choose the right circuit breaker? The Selective Coordination tool lets you quickly test various system and breaker combinations, allowing you to conduct preliminary analysis on the fly. With your product selected, you can configure and insert them into your design in seconds with our Layout Fast app. The Schneider Electric Consulting Engineer portal allows you to make quicker, better informed decisions that you can apply immediately to your project plan. Speaking of staying better informed, your portal is also an ever-changing information hub with continuous updates on products, industry news, and educational opportunities. A quick scroll through the homepage gives you instant access to our ARC Flash Resource Center with industry white papers, webinars, and analysis on today's most complex code issues. Technical specs, codes and standards, and a BIM library with small, rich product model files you can download. A powerful product FAQ tool for quick answers to your most common questions. A comprehensive white paper library with the latest engineering insights and best design practices. Up-to-the-minute industry news with continuous updates on events, tools, products, practices, anything relevant to your business. And to stay educated on all of it, webinars, online training, and meeting events to keep you current while allowing you to earn PDH, CEU, and other continuing education credits. When it comes to easy navigation and instant access to everything that improves both you and your projects, the Schneider Electric Consulting Engineer portal is your essential one-stop support center.